Welcome back to this interesting course on thermodynamics. This is a very important lecture, important in the sense that this is a lecture which applies the first law of thermodynamics to three important systems which we come across in real engineering life. These three systems are heat engine, refrigerator, and a heat pump. So the objectives here for me for this lecture is to apply the first law of thermodynamics to a heat engine, to a heat pump, and to a refrigerator. By application of first law of thermodynamics, what I mean is that I write an energy balance for a heat engine, I write an energy balance for a heat pump, and I write an energy balance for a refrigerator. And after writing this energy balance, I look at the thermal efficiency for a heat engine. I define a thermal efficiency for a heat engine, and I define the coefficient of performance for the heat pump and a refrigerator, right? So let us start with the lecture. This is a very simple schematic for a heat engine. So what is a heat engine? Heat engine is a system which operates on a thermodynamic cycle, and its job is to convert the heat to work. Okay, so what does the heat engine do? It converts the heat to work, right? So what you see in the schematic is as follows. What you see over here is, in this device, heat is being supplied from a higher temperature reservoir, that is, let us say, at TH, and that heat supplied is, let us say, Q1. And what does the heat engine do? The heat engine would partially convert this heat to work, right? So it converts partially the heat to work, right? And it rejects certain heat Q2. So if you apply the first law of thermodynamics to this, what you'll get is that first law means what? First law means an energy balance. What gets into the engine is equal to what goes out of the engine. So what gets into the engine? Q1 gets into the engine, right? So Q1 is the input, is equal to what goes out of the engine, Q2 plus W. So what goes out of the engine is Q2 plus W. So the first law is Q1 is equal to Q2 plus W, right? So just rearrange these terms, you will find that this work is nothing but the difference between the heat supplied Q1 and the heat rejected Q2. So Q1 minus Q2 is the work which is being produced by the heat engine, right? So we need to define now the conversion efficiency, which is also called as the first law efficiency or thermal efficiency. So thermal efficiency of the heat engine is the desired output, which is work, and the input, that is the heat input, that is Q1. So, okay, so using these notations, we have the thermal efficiency now defined for a heat engine as W upon Q1. Okay, look at the next important application, which is a refrigerator. Okay, you and me, all of you have seen this refrigerator. What does a refrigerator do? A refrigerator does a very important job of pumping the heat from a space to be cooled, that is a freezer section. Suppose this is a freezer section, right? So this is a cold section. This is cold section. The heat is being removed from this cold section. Let us say that heat removed is Q2, and this heat, this Q2 which is being removed, is removed because we need to supply certain work W. Okay, you run a compressor, you supply electricity to this refrigerator to run a compressor, that is nothing but the work's input is W, and as a result of which this heat is removed from the space to be cooled, that is from the freezer section, and finally this heat is rejected to the surroundings, which is hot relatively speaking, and this heat rejected is, let us say, Q1. Okay, so again, applying the first law of thermodynamics means what? Energy in is equal to energy out. So what gets into this refrigerator, represented by the term E? So Q2 gets into the refrigerator and W gets into the refrigerator, and what comes out of this refrigerator is Q1. So Q2 plus W, that is the energy in, is equal to Q1, which is energy out. So Q2 plus W is equal to Q1. So this is nothing but the mathematical statement of first law of thermodynamics applied to a refrigerator, right? Now the conversion efficiency. So for a refrigerator, we define a term called as coefficient of performance, which is nothing but what effect we get at what input. Okay, so what effect we get for a refrigerator is the refrigerating effect or a cooling effect, which is a desired output. So in this schematic, that is shown by Q2, which is the refrigerating effect. or the cooling effect. And for achieving this, we need to supply certain work W. So Q2 upon W, that becomes the expression for coefficient of performance. That is the refrigerating effect upon work, because refrigerator is a device which is aiming for the desired effect as the refrigerating effect or cooling effect. The third important device which you would be considering is a heat pump. Now, what is a heat pump? Heat pump will come across in colder climates, let us say in European countries, where we need to keep the room hot. Okay. And for keeping this room hot, we would employ the same components which are found in the refrigeration system. That means it will be a compressor driven system having the coils, indoor coils and outdoor coils. Okay. So what happens here is this device, which is driven by the compressor, would take the heat from the surroundings. It will take the heat from the surroundings, which are relatively cooler because it is a colder climate, colder regions. So the surroundings would be colder, and that heat would be pumped into the room, which is maintained at a higher temperature than the outside, because for the occupants to feel comfortable. Okay, so the indoor temperature is maintained higher as compared to the outside temperature, and this is achieved by employing a heat pump. So what does a heat pump do? The heat pump would take in this Q2 from outside. And why does it take the Q2? It takes Q2 because you are supplying work. So you are supplying work via the compressor. So Q2 is being pumped from this outside space. And this Q1, that is nothing but Q2 plus W, is pumped into this room, which is at a temperature T1, which is higher than T2. Okay. So the job of the heat pump is to supply Q1 into this room and maintain it at a temperature T1, and the outside temperature is T2, which is colder than the inside temperature. And for achieving this, we need to supply certain work W to the compressor. So if this heat pump concept is clear, so the energy flows are very simple now. So first law of thermodynamics, energy in Q2 plus W is the energy in into the heat pump, and energy out, which is Q1, right? And for defining the performance parameter, again, we use the term coefficient of performance, but that coefficient of performance term is slightly different from the refrigerator COP. Now, why is that so? Because in the heat pump, the desired effect is the heating effect. Okay, so the heating effect is what we are aiming for. So you're looking at this schematic, the desired effect is Q1. Okay, so Q1 is the desired effect, heating effect, and input is W, which is the input. So Q1 by W is the performance of the heat pump. Okay, so what we have looked at is, we have looked at the performance of the refrigerator, we have looked at the performance of a heat engine, and we have looked at the performance of the heat pump. How is the performance of a refrigerator measured? The performance of the refrigerator is measured by the term coefficient of performance. And how is that recorded? Coefficient of performance is nothing but refrigerating effect upon work. How is the performance of heat pump measured? The performance of heat pump is measured by coefficient of performance again, but in that case, the coefficient of performance is the heating effect upon work. And how is the performance of heat engine measured? The performance of heat engine is measured by the thermal efficiency or the first law efficiency, and it is recorded as the output, which is the work output upon input ratio. Okay, I hope these concepts are clear. In the next class, we will be solving numericals on this. Thank you.